Today, we've got Alice Caponiti with us. I'm not going to read all of Alice's bio because if I did that, she would not have time to speak. So I'm going to come to some of the highlights here. Alice serves as the Deputy Assistant Secretary for Reactor, Fleet, and Advanced Reactor Development in the Office of Nuclear Energy. She leads a diverse portfolio of research, development, and demonstration programs focused on the technical and economic sustainability of the existing U.S. fleet for commercial reactors and the development and deployment of innovative advanced reactors, including small modular reactors and microreactors. She previously led efforts to build, test, and design and deliver safe and reliable nuclear power systems for space exploration and national security applications, and conduct detailed safety analysis for each mission. Prior to joining the Office of Nuclear Energy in 2001, she worked on a non-proliferation program to reduce stockpiles of excess Russian weapons plutonium. Glad she got that taken care of with what's going on over there now. Mrs. Caponiti has been a bachelor's degree in civil engineering from the University of Maryland and a master's degree in nuclear energy and the technology and policy program from MIT. We're really honored to have her here and look forward to having her update us on kind of what's happening up in Wyoming now that we no longer have a nuclear plant in Colorado. Alice?
Hey, so first, can everyone hear me?
Yeah.
Good. Okay, great. Hey, so thanks for having me. And I know I was going to try to come talk with you guys earlier, but my schedule got overtaken by something else. So I'm really glad to be with you today. And I'm going to try to share a set of slides. Excellent. All right, great. So I'm going to be covering the role of nuclear energy broadly for our national goals to, transition to a net zero economy. And I will be able to hit specifically what we're doing in the state of Wyoming, but this is a broader treatment of the topic. And then, depending on your interests and our time, please let me know what questions you have. And I like to talk, and hopefully you'll find that out about me. But first, I wanted to give you a little bit of background about where I come from and how I came to nuclear. My civil engineering undergrad degree had an environmental focus. So I came to nuclear energy with that environmental motivation behind me, and I live my values. We heat our home with that fireplace. We heat a 2-story home and don't have a gym membership because we're always cutting and stacking wood. My husband, who's an electrical engineer, he and I installed ourselves 110 solar panels. I can't tell you, it's probably, I know it's 100 bags of concrete that's anchoring down that field array. And we've purchased an all-electric vehicle that we can power with the electrons that we make. But so I really believe in clean energy. This isn't practical for everybody. And what I'm going to talk about is the role that nuclear energy has in our energy mix that helps us have lower carbon energy for our nation. So we have a very ambitious national goal to help decarbonize our grid with an ambitious goal of getting to net zero on our electricity grid by 2035. That's a real challenge, and more broadly for our economy by 2050. And when we talk about the economy, there's many areas of our industry sectors that are very carbon intensive that we're hoping to help decarbonize with other sources of non-carbon emitting electricity. And just to give a sense of what the role that nuclear plays right now, our existing fleet of 93 power plants that we have on the grid today provide 20% of our electricity, but it's also more than half of our emission-free electricity. So our existing fleet is really important if we're going to achieve these goals. And we are doing work to help the existing fleet operate more economically so that they can stay on the grid. In addition, our nuclear fleet is highly reliable. The capacity, the availability factor of our plants is 93%. It's the highest capacity factor of any other electricity generation source. And also for nuclear energy, this sector is a huge job creator. In addition to about 50,000 direct jobs associated with our nuclear plants, there's 500,000 indirect jobs. They're an important employer in communities. And, oh wait, I have to do one thing before I lose you. And that is plug in my computer. Oh my gosh, this is really terrible. Okay, I showed up at the office without my power cord. If I lose you, I'm going to come back. So anyway, the electricity, the jobs offered by the nuclear industry is 50% higher those wages are than any other generation source. This just gives an example of the carbon emissions avoided by nuclear. It is relative to other sources of renewable energy. Nuclear energy avoids more carbon emissions on our grid today. We've talked about our existing fleet providing baseload electricity. Where we see nuclear operating in the future is in a variety of methods on our grid in combination with heat and electricity. And we see plants of different sizes. Our large reactors today are going to be partnered with smaller modular reactors and even microreactors. And so we can use this clean electricity to help desalinate water, to produce hydrogen, to help decarbonize chemical processing and industrial processes. And when we talk about the different sizes of plants, when we think about small modular reactors and microreactors, this gives you a sense of how much smaller they are than our existing plants. But what's more important than just the power sizes measured in megawatts is the attributes that they have. So for our large plants, these are large capital projects, a lot of construction to get them operating, whereas small modular reactors are going to have many major components that can be built in factories and shipped to site. And so these can be sited in places more flexibly than our larger plants. And in addition, they offer reduced construction times to be able to bring them online. And the modules can be added incrementally as the utility needs them to increase power in the local region. And for microreactors, these are plants that can be entirely factory fabricated and shipped to the site with minimal on-site construction. And both of our small modular reactors and microreactors have much enhanced passive safety that allow them to be operated and remotely monitored for more siting flexibility and enhanced safety for the region. So these are the attributes of these plants. And what I wanted to also hit on, and I'm frantically looking for my power cord, is that these are examples of why carbon-free electricity can be so important. In the upper left-hand corner is representing remote communities where just the cost of electricity can be 16 times higher than the national average because it's costly to deliver diesel fuel to regions that are not connected to an electric grid. And that amount of funding can be more than half the income of households in that region. When you look to the upper right, our data server farms, these data servers are more than 70 billion kilowatt hours needed on our grid today. And that's about 2% of our electricity output. In the lower right, transportation is now our largest sector of carbon emissions in our economy. It surpassed electricity production in 2018. And in the lower left, our industrial processes is a sector that employs 10% of our workforce and is a fifth of our greenhouse gas emissions. So these are all sectors where nuclear can have an important impact on helping achieve reduced carbon goals. And what I'm going to quickly cover is what are we talking about when we're thinking about small modular reactors? So enhanced passive safety, improve construction and operating costs, the ability to site these reactors in more regions not connected to water, and also being able to couple the power with other applications like use of heat. And so first I'm going to hit on the carbon-free power project. This would be the first deployment of the NuScale light water cooled small modular reactor that would be at Idaho National Laboratory. This is a 6-module plant, and it uses a lot of technologies that are common to our existing fleet today, but will be operated in a modular fashion. And this will be an example of using air cooling so that you don't have to have it sited close to water. If anyone knows what Idaho National Laboratory site, it's a very arid desert region in the state of Idaho. This first plant is scheduled for first operations in 2029. The Natrium reactor, this is going to be sited at a retiring coal plant in Wyoming. This power plant is 340 megawatts, so maybe a third of the size of a large existing plant, but it's coupled with thermal energy storage, which means that the reactor can operate at full power, but ramp the electricity output using the thermal energy storage from 100 megawatts to 500 megawatts over the course of hours, which means that if the grid demand is low or if the electricity prices are low, you can throttle back the amount of electricity onto the grid and ramp it up when needed. And when you don't need the heat to make electricity, you can use that heat for other economic products like hydrogen production or other operations that could be located near the plant to take advantage of that heat. So it offers a lot of flexibility. And then lastly, we have a demonstration project of a gas-cooled reactor that will be sited in the state of Washington near the Hanford Reservation and the Columbia generating power station. And this will be a 320 megawatt 4-unit plant that will produce high temperature heat and steam, which also can be used to generate hydrogen and other products in addition to the electricity. So these are 3 projects that are currently underway for first demonstrations before the end of this decade. And all of these plants have a lot of interest, not just here domestically, but looking at international partners who want to deploy this technology. And I think what's really relevant today when we look at what's happening in Ukraine and thinking about energy security, these are the kinds of products that we want US companies exporting and seeing deployed more globally for just better, more responsible power needs in regions. And so these are my key takeaways, understanding the role of nuclear in achieving our net zero goals, and that it is an important current source of our electricity, but the advanced reactors that we're developing will have these attributes to make them more flexible, more deployable, and more relevant. And then finally, that these plants provide important jobs for the community, especially when we think about communities that may have retiring coal plants, and that the loss of that important base and the local community could be impactful. These are technologies that come in and take advantage of that infrastructure and the workforce and make sense for our economy. So I talked really quickly because I'm still trying to figure out what I'm going to do with my low battery. But let's see if we can open it up for questions. And if need be, I can call in on a phone if my computer dies. How about that?
Okay, we have a question.
I actually have 2 questions. One question is, what is the status of fusion nuclear power? And the second question is that when something goes wrong in nuclear plants today, the fallout or the impact is really horrible. So what is the new technology that's being developed to combat such egregious situations when something does go wrong?
So that's a great question. So for these plants, well, first of all, our existing fleet nationally has an incredible safety record, and we have a top, like gold-plated regulator in the Nuclear Regulatory Commission. So first, I do want to make sure that people recognize the regulatory environment that we work in. For these advanced designs coming forward, when I talk about passive safety, what does that mean? Instead of relying on large pumps that require electricity from offsite if the plant needed to go offline, these plants entail features that would have natural circulation. So let's say a plant lost power, a grid went down. Instead of relying on pumps that have to be driven by diesel generators or something on site, just natural circulation, the thermal convections will cool the core and keep everything stable and cool without operator intervention. It's these kinds of safety features that are newer in these advanced designs, and how that's reflected in the safety is these plants have reduced emergency planning zones. It means that because of all of the safety in the site, instead of having 5 and 10 mile zones that you may want to evacuate from a plant if something were going on in an accident condition, that evacuation zone is much smaller and closer to the plant because of the fact that they take advantage of all these safety features and don't have the kinds of accident scenarios that we saw, for example, with Fukushima and other plants. So I've talked about the safety, and I think you had another question.
Yes, the state of fusion for energy development versus fission.
There's a lot of interest in fusion. The fusion technology is not at the point of having models that are ready to deploy commercially today. There is a great deal of investment in fusion for the future, but I see that as still probably 2 decades behind these fission plants in terms of their ability to be on the grid.
So speak to Wyoming and then possibly throughout the United States. All the coal mines, there's several of them are being decommissioned and slated to be decommissioned just because of, you know, all the issues and supply and pollution and age. Where are we at there? Is the push on your guys' side, that is our new model to replace the electricity from those decommissioned units?
So the Department of Energy's goal, so anything related to plant closures or what would be cited at them are local and regional goals. I see as the Department of Energy, our ability to support having technology available. And so in the case of the plant to be cited at Wyoming, we made an award to the TerraPower and Natrium team. And that team looked at where best to site that plant. So it was a local decision to site it at a retiring coal plant. And there's obviously a lot of benefits for doing so. And so I see for all of these technologies that we're supporting in terms of small modular reactors and partnering with companies to demonstrate them for first operations, and therefore having them available for future deployments makes them ideal to take advantage of the infrastructure at existing sites and taking advantage of the trained workforce. Some SMR developers have been studies to see how well the jobs and skills needed to operate these plants align with the types of skills and trades that already exist with coal plants. And when you think about nuclear, what's different about it? It's the way that you produce heat. Everything else about the plant, from operating turbines and producing electricity on the other side of that heat source, is the same. So there's a lot of commonality in terms of the skills and jobs needed, and then taking advantage of the transmission infrastructure at the sites and all of the other infrastructure that exists. So there's a really good alignment with this kind of technology source and where communities may have coal coal plants slated for closure.
Alice, can you tell us when the Wyoming plant is due to come online? And is that the project that's part of the Bill Gates organization?
Yes, so the TerraPower is designed backed by a company that Bill Gates is investing in. And then of course, PacifiCorp has Warren Buffett, I think, is a major investor. They're known to be rather visionary and recognizing putting their dollars toward solutions that are beneficial for society. So it's really exciting to be partnered with them in this technology deployment. That plant is slated to come online in 2028.
Could you maybe expand a little bit on Fukushima? And there's a widespread belief that there was just a significant or massive release of radiation over there. Could you talk a little bit about that?
For Fukushima, for that plant after the tsunami wave, what impacted that plant's ability to withstand operations was loss of their diesel generators. Those diesel generators were damaged by the water, and therefore they were not able to keep their plants cool. So when we talk about what it means to be passively safe, for these plants that I'm describing today have a lot of passive safety features that would have the coolant naturally circulating and the heat being pulled away so that they don't need those large diesel generators to operate. So it's a different kind of safety feature. I'm not familiar with the amount of radiation released under Fukushima, but I can tell you that the design of the plants that we are operating and looking to operate in the United States is a different posture than those plants that were in Fukushima.
So how are you going to solve the nuclear waste problem?
Yeah.
And how do you, I think it's more a matter of political will. And I haven't seen any talk about political will. There's a lot of solutions out there, but I worked at Los Alamos a while, so I know a fair amount about it. And it looks like political will is a problem, and without engaging the public on the issue and making it profitable for states to accept it or something, you have a hard time.
Yeah, so we have initiated a consent-based siting process for interim storage. And we just solicited input from the community broadly, and we have a website that shares information that we received on how should the Department of Energy approach interim storage with a consent-based siting process. Until we take fuel back as an agency, it is stored on site. Fuel is stored on site safely. For most reactors, when fuel is coming out of the reactor, it's stored in a pool to keep it cool. After some time, when a lot of that heat has dissipated, it goes into a dry cask for storage. These are large concrete cylinders. And for the plants that I just showed you, for let's say a 60-year operating life, the footprint of those dried casks will be like the size of a parking lot at the plant. And I really should have a photo of what that looks like. What does it mean to store fuel on site? If you think about all of the spent fuel from all of our reactors that have been operating all of these years, what that looks like is all of that spent fuel could be stored in an area of a football field, say, a football field, and I think like 9 meters deep, but you can kind of picture what that looks like when we're talking about spent fuel. So it's, all energy sources have, whether it's mining tails or, every energy source has a waste product at the end. What spent fuel looks like can fit inside of a football field, yet we have the responsibility to do something with that and take that from reactor sites. So we have a plan to store fuel safely on site, And we are restarting a process for looking at what does it mean to take that and have the government take responsibility for storage of that fuel. So that process is underway. It has been a political challenge, but technically it's a challenge that we know how to deal with that fuel safely and how to store it. And I realize that's not an entirely satisfactory answer, but hopefully that creates a visual of this, of the scale of what it is that we're talking about when we think about spent fuel.
This was actually a follow-up to the prior question, so he kind of stole my thunder. But basically, for the last 30 to 35 years, nuclear has been dead on arrival with regard to politics and regulatory environment. These are exceedingly exciting new developments that you've come up with. What is a realistic chance that all of these things can actually be implemented given that past political and regulatory environment?
Yeah, I think, you know, when you think about what's held nuclear back in the past, you know, we've got 2 plants under construction at the Vogel site right now, and those are large plants. And the United States hasn't built large nuclear plants in a long time. And those are big civil works projects. And a lot of what has been driving the cost and schedule with those Vogel plants has been just the fact that it's a massive construction project. The kinds of designs that we have now, where we can do factory-based component and have major parts of the supply chain shipped to site, that it's a much smaller capital construction project. And it's also a lot less capital risk for somebody to finance it, makes it easier to embark on these projects. And there's a lot of, I think, the size of these plants fits in well and is more easy to be added at the utility scale than, you know, multiple megawatt, 1,000 megawatt size plants. So I think the physical and design attributes of these plants make more sense for where we are today. And then you couple that with what I see as very strong bipartisan support in Congress for supporting these technologies. We see that in a lot of legislation being proposed that recognizes the value of nuclear energy as we think about where we need to go as a country with our, you know, not just our climate goals, but also thinking in terms of energy security goals. And, you know, I think what's happening in the world right now is a really good example of having energy sources that decouple us from parts of the world that we don't want to be as reliant upon, for example. So these are all things that I think have changed and how we can look at nuclear for broader deployments.
Hi, Alice. The plant in Wyoming, you said that's a coal plant that's being replaced with a nuclear power source. Does that change what that plant produces? I mean, will the service area that plant covers increase or decrease? And can you push electricity from, you know, the Wyoming-Utah state line to Fort Collins? Will we benefit from that?
Of the coal plant that's being retired, I don't know the exact power level, but I have the feeling it's on the order of the same size. This new nuclear plant will be about 350 megawatts electric. That tends to be the size of coal plants. I don't know about the specific coal plant that's being retired in Cameron. But in terms of how these electrons can benefit customers, that's when I was talking about the carbon-free power project that's going to be sited at Idaho National Laboratory, that plant is going to be serving municipal utilities from a very broad region that are pulling together and bringing that plant online to help a utility consortium for them. So I think in terms of how the how Pacific Core uses the electrons that will be produced at Camer is, I'm not really sure how that works and how far that reaches, but there is a lot of flexibility in terms of where to site a plant relative to customers.
So you've talked a lot about hydrogen storage, and as a person that's done some compressed gas work, hydrogen is a nasty thing sometimes to store, and you have to worry a lot about safety. And then storing a bunch of that on site, isn't that creating a hazard that might be better off site from a nuclear plant? Or
There's actually, with our existing fleet, we have a number of hydrogen demonstration projects underway right now. So with our existing plants, they're shutting down today, not because they're hitting the end of their licenses or because there's anything mechanically wrong with them, but because economically, they're competing with the cost of low cost of natural gas and some other economics that are making those plants challenged. And so one of the things that the industry is doing is looking at doing something else with the heat that brings an economic product like hydrogen production. So for example, at one plant in Ohio, it's really close to a hydrogen powered bus fleet in Toledo. And that bus fleet needs hydrogen. The plant can produce hydrogen. So being able to produce hydrogen and store it safely in the context of a licensed plant is something that can and is being done. I should probably become better versed in the mechanics of hydrogen storage. I am not, but based on that question, I will look that up and have a better answer for you next time. But there's a lot of interest in hydrogen production, not just in terms of the direct use of hydrogen, but also having it be something that can be transported to where it's needed, where it's harder to transport heat. Hydrogen is something that can be transported to where it can be used. But I will have a better answer for you next time.
You mentioned desalinization. Now that we're running out of water, and especially all of the coastal regions around the globe, do you see these smaller megawatt units being produced or will being produced in areas like Southern California? They've got the ability, but it's very, very expensive. But they're going to need to do it.
So for these advanced designs, particularly for the one that's going to be sited in Wyoming, and then the other one that I talked about, the X Energy plant that will be sited in the state of Washington, those power plants operate at higher temperatures and have higher temperature heat as a product. And it's that higher temperature heat that provides a lot of flexibility of using that heat for desalinization. It can be used to, there's a lot of ways that you can produce heat that when you think about today, we may burn diesel generators to get the heat for industrial process, where now we can use heat generated from nuclear. So, and the fact that these plants are smaller kind of make them well suited to bring where they're needed locally. So for a small modular reactor to have utility customers for electricity, they can also be sited in combination with processes that can take advantage of the heat directly, like a desalination plant. There are parts of, I'm trying to think of some of the conversations we had. I think in Texas, there's aspects of drilling and cleaning the drilling fluids with water that can be a very carbon intensive process that they would look for a nuclear small modular reactor to provide that heat and just make those processes much cleaner. So I think it's the siting flexibility coupled with the flexibility of what you can choose to do with the heat, with desalination being one example.
I have a question about with severe weather situations becoming more common. Do the architects or the engineers, are they thinking about building those plants either with different materials or with different designs to withstand these more common weather occurrences?
Yes. So these plants, so one of the methods that, so all of these plants are being designed with the seismic requirements of the regions where they will be sited. That is a given. Other innovative features of the plant design are, for example, for the portion of the reactor is siting those below ground surface so that they are kind of surrounded by the ground for heat transfer and just for protection of environmental hazards. And we've talked about the fact that they don't need to be located close to water as a requirement. So ensuring that they are, out of the way for floods. So there's a lot of features in the design that make them really robust.
Okay. Alice, thank you so much. You are very knowledgeable, and you can handle all our questions. That was great. We thank you for joining us today, and also admired how you recovered from that loss of power.
Thank you. It's thanks to my iPad, which does not have a power cord. And again, I apologize for that. I was parked in somebody's office without my power cord and didn't notice it until my warning started going off.
Yeah.
It's all about electricity.
Great job. Great job. It is all about electricity.